Hello there. So this is video number 2 of section 4.5. So earlier this section, we introduced dimension and the dimension of a vector space, right? Because we saw that every vector space, or every basis, I guess, in every vector space has the same number of vectors. And so we associate with each vector space that number called the dimension, right? So for example, the dimension of R3 is equal to 3 because every basis of R3 has 3 vectors. A little more confusingly, the dimension of the polynomials of degree at most 2 is equal to 3 because we have to account for the constant polynomial. So this video, I want to talk about the dimension of subspaces. And so this theorem will give us sort of insight. Again, this theorem is important, but it will give us insight to really prove sort of a big theorem at the end of this video called the basis theorem. Any theorem that starts with the word the, has to be important. The only thing that could be, if it starts with the word the, it's important. But if it starts with the words the fundamental, then it's just really important. So like the fundamental theorem of calculus, for example. I don't know if there's a fundamental theorem of linear algebra. There might be, but I don't know what it would be. Anyways, we've got H, which is a subspace of a finite dimensional vector space. V, here finite is really important. I'll talk about why here in a second. And we're assuming that V has dimension n. Then what we say is that any linearly independent set in H can be expanded into a basis for H if it already isn't one, right? So certainly if you have a linearly independent set in H that is a basis for H, then it can be expanded into a basis for H. What this is saying is if that you give me any set of vectors in this subspace, right? And this set of vectors is linearly independent, what this sentence is saying is that I can basically add on to this current set, right? So as a brief illustration, right? Let's say I had like the set V1, V2 in H, and this was linearly independent. What this says is I could start with this set and just continue adding vectors until I got a basis for H, right? So basically what this says is you could start with the any linearly independent set, keeping that original set intact, you can just add on to that and eventually get a basis for H. And so then what it says, and this part of the result to me is fairly intuitive, I think, that if H is a subspace of V, remember that means H is a vector space that is contained in a larger vector space V, well, then the dimension of H has to be less than or equal to the dimension of V. And this part here is why we have to assume that V is finite dimensional, because if we're working with these numbers being infinite, right? Like if the dimension of V is not finite, then this greater than, less than, or equal to doesn't really make sense. So, like we've sort of been doing, there's the proof sort of outlined in the worksheet. So again, there's like a couple questions that working through them, you'll kind of come to the proof. So I'd highly recommend thinking about those and working through those, and then I will talk about each one and the proof of this theorem. All right, so I've broken this down sort of into 2 steps. So the first step, what we want to do is consider some linearly independent set in H. So we're going to let U1 through UK be linearly independent. And we'll specify that these vectors are in H. And so we'll call this set, actually even easier, we'll call this set S just for easier reference. So this original set is S. So notice S is linearly independent, right? So if the span of S is equal to H, then there's nothing to show, right? Because this means that this set is already a basis. So what we want to do is assume that, so notice here, if the span of S is not equal to H, then the span of S is a subset of H, right? Because this sentence is true, because certainly all of these vectors are contained in H, right? And since H itself is a subspace, that means H must be closed under all linear combinations of vectors, right? So all linear combinations of all sets of vectors in H must be contained in H. And so this set, the span of S, is a subset of H, but it is not equal to all of H, right? And so what this means is that, and so this is sort of the answer to number 1 now. So because span of S is not a subset of H, there is a vector in H, and for convenience, we'll just call this vector u sub k plus 1 in H that is not a linear combination of the vectors in S. And so that just means, right, that, well, this is a linearly independent set, right, because none of the vectors in this set can be written as linear combinations of each other. And this means that I can just tack on this remaining vector u sub k plus 1, and this set is still linearly independent, right? Because what happened is I just added a vector that couldn't be written as a linear combination of any of these. We already knew that these were linearly independent, and so this slightly larger set is also a linearly independent set. So I'm going to keep this on the board because basically the way this proof goes is we're just going to continue to repeat this process of adding vectors to this set until we can't anymore. And so this will be basically the answer to 2. So we've got, right, so, right, what we did is if the span of S was not equal to H, right, we found an extra vector we could add. So the question you might ask, right, is, okay, so I just added this vector, right? How do we know that I can't find yet another vector? Well, we don't know that, right? Like I might be able to find yet another vector that I could add that would make, you know, this even bigger set still linearly independent. So what I need to do is show that at some point I can't add any more vectors. We'll say any more linearly independent vectors to S because we know that V is finite dimensional, right? The dimension of V is less than or equal to n, and S is a subset of V. And so why is this all true? Well, remember, because V has dimension n, right, that n also restricts the size of the largest possible independent set in V, right? So I know that this set S is in V, and at some point, right, it's in V, it's also in H, but remember H is contained in V. At some point, I'm not going to be able to find more vectors because if I found more than n vectors, right, that were linearly independent, this would contradict the assumption that the dimension of V was equal to n. So at some point, if I keep repeating this process, there will be no more linearly independent vectors left in H. But at this point, S is a linearly independent set. And, well, what did we just argue? I can't find any vectors in H that are linearly independent from this set that I've just been adding on to. Well, that means that every vector in H can be written as a linear combination of this new set, and so the span of S is equal to H. And so this proof was sort of just the very almost unnecessarily confusing mathematical way of saying, if you have a linearly independent set, just keep adding on to it until it becomes a basis. And that's what this theorem says we can do. And so notice, of course, that the dimension of H is less than or equal to the dimension of V, because certainly any basis for V must also be a basis for H, right? And so, well, any basis for V must also span H. I guess it won't necessarily be a basis for H, but since H is a subset of V, this part sort of just follows immediately that, right, I can't possibly find, actually, it's sort of encoded in this step as well, that I couldn't possibly find more than n linearly independent vectors in H, because we've already assumed the dimension of V is equal to n. And so this just sort of follows from the fact that H is a subspace of V. So, all right. So now we can prove the basis theorem, because the basis theorem will basically just follow immediately from what we just proved. And so what this tells me, in fact, is that finding a basis in a vector space V might be easier than we had originally thought, because it turns out if V is a p-dimensional vector space, well, how do I find a basis for V? I just take any linearly independent set of size p forms a basis for V. Not only that, let's say maybe I didn't know my set was linearly independent. Let's just say I knew that my set of vectors spanned V. A set of vectors, we'll say set of vectors in V spans V. And we'll explain that correction in a second. If a set of vectors in V spans V, then it must be a basis. So, the first statement here says that if I take any linearly independent set of p vectors in a p-dimensional vector space, that set must be a basis. And that just follows immediately from theorem 11, right? Because if V is a p-dimensional vector space, every basis for V must have exactly p vectors. If I've found, right, so if I found, we'll write out the proof of this on the board. So if a set of p linearly independent vectors in V is not a basis for V, vectors, then we can add on to it by theorem 11. But this contradicts the assumption that the dimension of V is equal to P. Right? So basically what this is saying is that if I've got a set of P linearly independent vectors in V that is not a basis, well then I can find some vector in V that is not written as a linear combination of my vectors in this set. But remember, the fact that V is p-dimensional also implies that the largest independent set in V can have size p. Right? So this is saying if I take a maximum independent set in V, well, certainly I can't find any vectors then in V that are still linearly independent from that set, meaning that set must be a basis. So the second one, if a set of vectors in V spans V, then it must be a basis. This sort of follows in the same sort of logical steps that, right, if I have a set that spans V that is not a basis, well, that means that it checks off the first quality of being a basis, right, that it spans V. But if it's not a basis, it means it doesn't check off the second quality, meaning that I've got a set of P vectors that spans V that is not linearly independent, which that means we could sort of go the other direction with it, right? We could remove a vector and find a set of P minus 1 vectors that spans V, but that would contradict the fact that V is p-dimensional because, as we now know, every basis in V has to have size P. And so this tells us two ways now of finding a basis that we didn't officially have any linearly independent set of vectors of size P, or maybe even stronger, the second sentence, any set of vectors that spans our vector space immediately a basis, which is, I think it's awesome, right? Like, you don't even have to check if the vectors are linearly independent. You just so like, okay, these span the vector space, we're good. So anyways, I'll finish up here with a couple of examples. These are on the end of the video 2 section of this worksheet. So first thing we want to do is find the dimension of the subspace spanned by the following set of vectors. So I've got 4 vectors of length 3. So what we want to do, we're going to use a matrix, and here we actually will only need, since we're looking for dimension, we'll only need to reduce it to row echelon form, because notice that the subspace spanned by this set of vectors is going to be the same as the column space of this matrix, right? So we just need to figure out the dimension of the column space of this matrix, which we know how to do. So 2 R1 plus R2 . So whenever we get rows that match up that much, I tend to feel like I've probably done something right. Although I guess it could just be a coincidence, certainly. All right, so this matrix is now in row echelon form. So what we want all of the columns that correspond to pivot entries, right? So that will be column 1, column 2, column 3. So that means a basis for the column space of this matrix is given by rows 1, or columns 1, excuse me, column 2, and column 4. And so that means that the dimension of the space spanned by these 4 vectors is equal to 3. Which, right, we knew going into this, since these were all vectors of length 3, that the dimension was going to be at most 3, certainly. But, you know, it could have been less than 3, certainly, if more of these vectors were linearly dependent. All right, so number 2 is a little more interesting. Well, they're both interesting, I guess, but number 2 is kind of cool, because number 2, we're given this set of vectors, and we want to extend we'll sort of see the power of theorem 11 here. This set into a basis for R3. So what theorem 11 tells us, right? So certainly we can eyeball these vectors and see that they're linearly independent because they're not scalar multiples of each other. And so what theorem 11 tells us is that all we have to do is find a single vector that is linearly independent from each of these vectors, and we'll be able to extend this into a basis. And so in this case, I can just pick my favorite number, which happens to be 2, and add any vector I want that is linearly independent from these 2 vectors. And looking at these 2 vectors, they both have a 0 in the second entry. And so notice all I have to do is just add this 2 here into the second entry. And this is now a basis for R3. Well, how do I know that? This is 3 linearly independent vectors in R3. We know that R3 has dimension 3. Therefore, by the basis theorem, this is a basis for R3. All right, so next lecture is going to be video 2.5 of section 4.5 and video, it's basically a little bit of 4.5, mostly 4.6. So I guess technically we'll move into 4.6, but yeah. We'll learn about the rank nullity theorem, which is also really, really cool.